October 2010. A new dawn breaks over India. It is the focus of the whole world as it unfolds a grand spectacle. New Delhi is a venue for the Commonwealth Games 2010. And Jawaharlal Nehru Stadium is the crown jewel. Hosting the Games for the first time, India could use this event to showcase her talent and capabilities, reflecting her new global mood. Let's travel behind the scenes to see how it was made possible. The challenge was in constructing the new superstructure that was to be created around the old one.
The motivation was to create an icon for the Commonwealth Games in 2010, and since we had to work with an existing structure, the idea was to build an envelope around the existing structure, build a new facade which keeps the existing structure visible behind that, but creates the envelope to show this is new, modern, and this is the modern India and modern Commonwealth Games. The solution here was to have a spokeswheel-based system.
Actually, when we got this project, we probably did not realize the complexities of the project. We realized that it's much more difficult than we thought. The most logical thing was to put up a team together, good team. And actually, Indian engineers are better than anybody in the world, not less than anybody else on the site execution and all. And they did a fantastic job.
The 4 lighting towers that jutted out were to be dismantled. The old stadium had different radial ramps outside the stadium, which were to be dismantled to give the stadium a new shape. To accommodate the towering steel structure in the design, it was necessary to build new foundations to support it. It had to be independent of the older structure, as it was too weak to support it in any way. In technical terms, the structure has piles as its foundation, a total of 272 piles, each of 1.5 meter diameter and 25 meters in depth. Each pile has approximately 46 cubic of concrete and around 3 metric tons of steel. A group of piles have a pile cap and shear wall, which is an H-shaped concrete structure which directly supports the steel structure.
It's iconic engineering and iconic architecture. It's a monument. It's an icon for the time we work and live in. Innovation develops from project to project. It's a very sophisticated project. It works.
The fabrication of the columns was commenced on site. Special grade steel was sourced. One of the most novel engineering ideas was the jigs used for fabrication. It made the work handy and quick-paced, thus reducing time consumption to a large extent. The length of each column and compression ring is huge and could not be built in one time. Thus, these columns were made in different boxes. 2 boxes were joined with butt welds using rotators. Rotators and high-quality welding machines ease the welding of 528 boxes to create the massive V and X-shaped columns.
Right from the procurement of material, we have maintained the quality. Our material, this is a special type of steel. It will not decay because it has got good corrosion protection, and moreover, under the load, to have its ductile strength, we have maintained the sulfur content 0.005%. 100% ultrasonic testing has been done for all the welding.
The top of the V and X columns were joined by the lower compression ring, LCR, and upper compression rings, UCR, respectively. To join the various sections of the ring, end plates were needed at the end of the boxes to connect them to each other. The parts of the end plate were precision cut using CNC, computerized numerical control equipment. To ensure an exact fit of the end plates, these end plate holes were bored in pairs, as about 39 holes had to be matched for bolting. As this is an unusual structure, a high accuracy had to be maintained in the fabrication of the steel. Guidance was taken from a German consultant and DIN codes were followed, which are tougher than Indian codes. Following these codes, an accuracy of less than 1 millimeter as required was maintained. The different parts were welded together using saw or submerged arc welding technique, and 100% of the welds were tested using multiple methods like ultrasonic test and dye penetration test carried out by third-party external agency. The ends of the boxes were cut using plasma cutters, the end plates inserted and welded into place. The welding made the plates deform. Therefore, the surface of each end plate had to be finished perfectly straight and smooth. They were ground to a mirror-like finish so that there were no gaps between two end plates. A maximum of 0.2 mm gap between the end plates was maintained in the fabrication shop. To achieve the strict requirement of accuracy and shape, each element went through a trial assembly and the results were compared with the required conditions before they were mounted on the columns. Total stations were used to measure the dimensions of the elements and correction for temperature variation was also done.
Actually, this project, right from the word go, it was quite a challenge right since then. Every aspect here was in stages. And as in any other construction field, there are generally activities which go in parallel. But here in this structure, if you see, every activity was a series activity, and any delay, any hiccup in one activity hit the entire project. And then a company like Shapurji, which put in every effort, gave probably the biggest financial support here, which made this probably happen.
The X and V-shaped columns were fixed with a concrete structure with special types of bolts which are known as single tendon bars. These bolts were imported from SAH Germany and were fixed by the specialized team from VSL.
In these foundations, you can see some anchor bolts are there. These bolts are specially ordered to Germany, SAH. It can take a load of 60 tons. Workmanship also, we have maintained it very high standard. Otherwise, this structure would have not been possible.
With the fabrication of the V columns finished, the erection of these columns began. The V columns were hoisted using two cranes simultaneously. The lower part aligned to the base plates embedded in the foundation and held into place by anchor bolts. It was hinged to the base plate and required structural support to prevent it from falling. Then the end plates of the compression ring were meticulously aligned and bolted into place. Additional supports were designed and erected along with the V columns to give the structure the much needed stability. As till complete erection of all the 44 columns, the structure would not be stable. The V columns came into place one by one and eventually completed the inner ring.
First of all, it's a great day for all of us to see that, let's say, 40% of 50% of the structure is being built now, and it fits. You see, there's no gap, so technically it's fine. It's been a long way, and we had to face a lot of problems, and not only during design, but also during execution, of course. But in the end, it's teamwork, and if we proceed like that, there's no worries that the Commonwealth Games will have a new stadium.
The larger X columns of the outer ring are 36 meters in height, so they were difficult to move when made in one piece. Therefore, these were made in multiple pieces and then joined together at the erection site. Multiple columns were laid on the ground and welded together to form the huge X columns.
At the start of the project, we planned in, as was in the tender stage, as in do it in parts and pieces. Then while doing the fabrication, we realized that is not possibly possible. Then we came up to a solution that we'll do it in two pieces. Then again we came up to a solution right before erection that no going into two pieces, we'll do it in one piece. That was probably what I would say is one big challenge wherein we overcame, and then we continuously improved ourselves, improved the methodology to come into a situation wherein we got it right the first time.
One step which is not normally done. That 100-ton member was put up in one go only. We did that dry run on the ground where we connected three pieces on the left and right, and the middle piece was lifted. Our fabrication associate and our engineers, of course, I think main credit goes to both of them. they found ways to do it differently, not as the consultant said, rather tried their own hand. CPWD also had been very supportive to us on that.
The pre-prepared compression ring segment was attached to it and the pieces were painted and finished. The top of the compression ring had a walkway with safety rails attached to it for the workers to be able to work on it once the ring was in place. The mammoth task of lifting this giant structure was like a choreographed dance sequence which took great preparation. The dancers here being the 4 massive cranes, each one of different load-bearing capacities. Detailed planning was essential. The earth surrounding each crane was scooped, paved and leveled, providing a stable base for the immense loads they were to bear. The 4 ends of the X column were then attached to a crane each and hoisted into the air. The cranes had to move in a choreographed manner, requiring constant guiding and coordination. With a structure so big and heavy, suspended in the air by 4 cranes, there was no room for mistakes. The lower legs of the structure were aligned with the base plates, but they did not slide into the slots of the base plates as expected. They were a little wide. Ingenuity struck as a chain block was used to bring both the legs closer. Successfully, the 2 hinges slid into the slots and were quickly bolted into place. Before the top could be secured with support, disaster struck in the form of a summer squall. So there was a 36-meter-high X column weighing 120 tons, bolted at the bottom, but at the top suspended by cranes, dangling in the storm. A very daunting sight, certainly not one for the faint-hearted. As the X columns were erected one by one, other than interlocking with the next one, each column was provided with additional structural supports, like in the V column. The uniqueness of the design is to accommodate the distinct advantages that it provides. It has an inherent and built-in strength against earthquakes and rare wind loads.
So during the time of earthquake, if it happens, this structure will move. Moreover, this structure is designed for a movement of 300 millimeter. This much sway they can give. This cable, with the air, with the wind, it can go up to 1 meter up and 1.5 meter at the bottom.
The base hinges mentioned earlier have a significant function during an earthquake and also in the expansion and contraction during the extreme temperatures of summer and winter. Not only the base of the columns, the ends of ring elements are also pinned to the columns, allowing the ring elements to adjust themselves as and when the steel expands or contracts, and also when the cable is being stretched. When the ring was complete, the geometry of the design is such that it becomes a self-supporting structure. Only then, this gigantic steel structure, weighing 13,000 metric tons, became balanced and safe. With all the X columns in place, the gaps between the head plates brought to acceptable limits and the overall geometry approved, the structural supports were removed.
The biggest hurdle which I remember was that matching of these head plates. We could achieve up to an accuracy of 3 millimeter, but the German consultant said that it should be 0.0. We got some German specialists from there and who came here and used some other technology which we are not aware of and got those gaps closed. And finally we could achieve all 920 meter and we could close all the gaps in 0.0 accuracy. That was, I think, the biggest thing which was there. But there are quite a few more. But with a positive approach from the management and the company and the owners, especially Mr. Cyrus Mistry, I think it was possible.
The final roof has 2 components. One, a cable framework or net, which is about 450 metric tons of high-strength cables stressed into position, and 2, 54,000 square meters of PTFE fabric, which is basically Teflon-coated glass fiber cloth.
This entire structure which you can see on top is based on a compression ring, which is the largest compression ring here, is almost a kilometer long. And the accuracies are such which we had to achieve, but the total length, finally what we achieved is within 100 mm of the total length required. To get this, we had to develop a lot of processes. And I believe these are some of the processes which will become an industry norm, which people will look and follow.
These cables were sourced from Pfeiffer, Germany, and they arrived coiled up in big boxes. The trucks carrying them could enter the site only at night, as the stadium is located in a highly restricted area. The whole cable net had to be lifted simultaneously into its final position, so it was laid in the required pattern on the ground first. Cable laying was the most tedious of all the tasks due to the complexity involved. However, it was dealt with in the same spirits, giving way to some innovative engineering skills.
The lifting of the cable was a big task. These individual cables are of 60 meters in length, each cable, and all of these cables were in coils. And generally, internationally, they're used to using high, big cranes, but here in India, we have a big advantage of labor, and thoughtful and mindful labor, who, if guided properly, can do a great job without those huge equipments. Instead of that huge crane, use some hydras, a combination of hydras and a ropeway kind of system, wherein we pull these cables from the floor instead of taking it high up in the air and hanging it down straight.
Once the inner ring cables and the radial ridge and valley cables were laid, the ridge and valley cables were pulled from the center to the edges. One end of these radial cables was connected to the inner ring on the castings, and at the other end, the castings were secured firmly in place to attach the jacks to them, which would eventually pull the cables to its position. All the castings used to join the various cable segments together to create the cable net and to support the membrane over it later were fixed into place on the ground itself. Huge hydraulic jacks in multiple numbers were used for this heavy lift, as a huge amount of force, equaling to a weight of 100 MiG aircrafts, was to be induced into the cable system to get it into its final position. The lower valley radial cables were attached to a single 70-ton jack, whereas the upper ridge valley cables were attached to two large 120 tons jacks at the pulling end and were secured to the inner cable ring at the other end. With all the cables secured and attached to each other and the jacks, the moment of truth had arrived. It was time for the lifting of the whole cable net, which is a slow and tedious but precise and highly risky job. All the jacks attached had to pull simultaneously at a very specific rate, as there was the permanent danger of the cable net being lifted into a lopsided position. The design of the cable structure is on the same basic principle of a bicycle rim, where steel spokes create tension and keep the rim in compression. Similarly here, the radial cables act like the spokes in the bicycle rim, and the structural steel beams on the X and V columns act as the rim under compression.
But on this kind of a structure, which is, everything on pins and which is flexible, and then also very accurate, because the cables which we have got here are all fully locked, meaning the length of these cables is fixed and these cables cannot be altered in length. We just have to get our structure to a place wherein the cable would get pinned. So accuracy of the structural steel was a big issue, and I believe we were up to the mark in it.
During the cable lifting process, the whole structure would shrink when the cables were being stretched during the lift. So the whole geometry of the stadium would change after the erection of cable net. Since this type of cable net was being erected for the first time in India, and as it would induce huge amounts of stress in the structure, a highly specialized team was involved. Despite the challenge of the methodology, the cable net was lifted perfectly. Where the valley cables were pinned into LCR and ridge cables were pinned into UCR, resulting in a cable net ready for the membrane. The PTFE membrane was sourced from Saint-Gobain, USA, and then fabricated into shape in Mexico. This fabric is one of its kind, and its manufacturing involves an explicitly unique technology. The avant-garde membrane is highly stretchable and fireproof by virtue of the material it is made up of. A unique self-cleaning property is possessed by the membrane. Thus, it doesn't allow dust and foreign bodies to stick to it. Off-white in color when installed, the membrane gets bleached in UV rays and becomes whiter with each day of exposure. A total of 200 skilled workers were used for lifting the membrane panels. The workers were trained and specialized to work at heights using rope access system. Special type of lightweight aluminium swing stages was imported from China to facilitate the work at heights.
The next biggest challenge was the membrane itself. Pulling this 600 square meter panel was not an easy task. And the agency which we hired, which we depended upon, Tayo, also had quite a big experience doing these kind of structures before.